Swayam Prabha. Digital India. Educated India.
And welcome back to this lecture series on foundations of cyber physical systems. So, in the last lecture I believe we covered some of the Lyapunov stability theorems, and we discussed about the basic direct methods and also the indirect method. So, today we will start with the last theorem in this part of our coverage, which is this theorem 4. So, let us just directly get into the statement of this theorem. So, what this says is that like all our previous cases, we are considering this origin as the equilibrium point for autonomous system which is just specified using this function f, okay, which is a continuously differentiable map with d is defined in this domain d. Okay. Now, we will do something new here, which is like, let us consider that we differentiate this function with respect to x in the state space, okay, and then evaluate it at the origin, okay, and that gives us a matrix A. Okay. So, we will say that the origin is asymptotically stable, okay, if we consider that the real part of this I mean eigenvalue lambda I is less than 0 for one or more of the eigenvalues of A. Sorry, this should be it is of course less than 0 for all of the eigenvalues of A. Okay. So, as you can see, that is just our basic idea of stability, right. What we say that, well, for any linear system, let us say my system originally was x dot equal to A x, and for this to be stable we want that, well, for A whatever are the eigenvalues, let us say lambda I, lambda j, whatever are the eigenvalues, for all of them we will need that their real parts are negative, right. So, the eigenvalue may have a real and an imaginary part, and for all of them the real part should be negative, right. So, that was our requirement. What this theorem tells us is that, well, this idea can be generalized. We can consider any autonomous system and we can kind of linearize their system around the origin to obtain this matrix A. And once we do that, for this matrix A, the same thing will hold. That means, for this, as long as for all the eigenvalues of A, we can show that we can actually see that if for all the eigenvalues of A, if the real part is negative, we can say that the system is asymptotically stable at the origin. Okay. And that would also mean the other thing that, well, if there exists some eigenvalues, if there exists some lambda I for which the real part is positive, then the origin is unstable, right. So, that is the idea. All we are saying as these are standard stability results, right, that for all the eigenvalues they have to have negative real parts to be stable, and if any one of them has a positive real part, then it is unstable. We are saying that, well, that idea can be also applied to this domain of nonlinear systems, as long as you can obtain a linear matrix a matrix representation for that, whereby by differentiating the system at the origin. So, fine, let us try and create a proof for this using our Lyapunov style of arguments here, right. So, we started with this, and then we said that, well, we linearize it, right, at the origin, and that gave me this representation A, right. Now, if A is Hurwitz, So, this is the linearized version, and we can say, applying our previous results, that as long as A is Hurwitz, then for this linearized system, as long as we can figure out a P, I can always which is basically symmetric and positive definite, we can have this V equal to x transpose P x as a candidate Lyapunov function for this linearized system, right. Now, what we want to show is that, well, under what conditions this V can also be a candidate Lyapunov function for the original nonlinear function f around the origin. Let us see. So, this is my original system, and for this system we want to see that, well, if V x can be a candidate Lyapunov function. So, this is the question. Okay. So, let us try one thing. So, this is my original system. Now, let us break it into two parts, the first part being the linear part, and this is the residue. So, let us call this residue as g x. Okay. So, for this V, if I take a derivative now, a time derivative, let us see what we get. So, x transpose P and then you have x dot. So, that becomes f x here, right, because x dot is f x, plus what do you really have? You have x dot transpose, right. So, that will give you f x transpose, right, times P x. So, basically instead of A you are having f x here, right, while doing this derivative of the Lyapunov function. So, now let us try to bring in the linear and nonlinear parts here. So, I can write these two together gives me this first term, right, and then I have f x transpose P x. So, that is what we have. So, this transpose can go in. Now let us see what is Gx transpose. Yeah. I mean, we should be able to write this as like this. So, if we apply the matrix Lyapunov equation, we can write this as a minus q to Gx. So, that is what you have, right. Now, let us observe some property of G. So, what we can show is something like this. So, let me delete this part here. The norm of Gx, so second norm to be more specific, by the norm of x, this will tend to 0 as the norm of x will approach 0. So, the point is, I mean, this is obvious, because if you understand what is Ax from the definition, so Ax was the linearization of fx itself around the origin, right. So, that means when x is approaching the origin, the function Gx is going to be infinitesimally small, and that is why in the limit condition, when I have x approaching 0, this ratio would also be approaching 0. Okay. So, what we can say in such cases is that any positive scalar for this, there exists some other scalar r which is also positive, such that this norm So, this is it. So, for any scalar, we can find another scalar r which is sufficiently small, so that the moment I have x less than r, this value of g would be bounded, upper bounded by gamma times x. So, for any such gamma, I can find a suitably small r, so that the moment the value of x is approaching 0 and it is already less than r, I will have the value of Gx small enough to be upper bounded by this gamma times x. So, I hope it is clear that we are trying to linearize around the origin. So, the function is approaching, the function fx is approaching towards x, and the residue Gx is also approaching the origin. And when x is sufficiently small, we can always figure out some upper bound, some lower bound, some upper bound like this, that when x crosses that, then I can bound this value of Gx by this gamma times x. Okay. So, this is coming from the continuity of these functions, and what we can show as such is, well, we can then write since I am able to bound Gx by gamma x2, so I can then replace this Gx by this upper bound, and I can then say that, well, derivative of x, which derivative of Vx, which is less than, which is equal to minus q plus this containing Gx, should be less than the same thing where Gx is replaced by the upper bound, right. Sorry, here it is x transpose qx, right, because the matrix Lyapunov equation, what it will do is, if you remember, if it is if we apply it here, it was minus q equal to this P A plus A transpose P, right. So, that is where it gets applied. So, this part becomes, this part is what becomes q, and x transpose and x remains. So, that is minus x transpose q x. So, this remains here, and this G x will get upper bounded. So, what we get is plus 2, and you are replacing this G x with this upper bound, right. So, the upper bound being some gamma times this, right. So, this will technically give you the second norm square. So, let us understand what just happened. So, this P was there, right. Now, G x gets replaced by the upper bound, right. So, and that upper bound is I mean gamma times x, right. So, then essentially this is a scalar, right. So, you will have this 2 and x transpose and the x together will give you the norm, and you have the value of P here in its scalar form, which is the norm, right. So, this is how you get the upper bound, but you also have some other facts there which we can apply. So, we will apply this well known result from matrix algebra, which is that we can show that this thing x transpose q x, this quadratic form. So, one thing let us understand, this will eventually give you a scalar, right. So, this has a well defined upper and lower bound, and it is bounded by yeah. So, given this quadratic form x transpose q x, if lambda mean of q and lambda max of q represent the minimum and maximum eigenvalues of this matrix q, then for x transpose q x we have a well defined upper and lower bound. The lower bound is x mean, the lambda mean times this x's norm, and the upper bound is lambda max times the x's norm square. Okay. I mean on both sides is lambda mean times x norm square, and its lower bound is lambda mean times x norm square. Okay. So, we can actually apply that constraint, and we can actually show that, well, if this is true, then if I apply this part here, and if I replace this with an even smaller value, right, then I can say that this is even less than yeah, and this all holds for this condition, that is for all values of x, so that the norm is less than r. So, once we are inside this r radius ball, we bring x inside this r radius ball, we have this condition holds, that holds because of this, because as we approach more towards the origin, this component will approach 0, right. So, this holds, and from that we can write this. Basically, we are replacing, we are applying this condition to this, and then we are applying this lambda mean bound here, and we get this condition. Now, what does this mean? That this means that I can actually make a choice of gamma here. I can actually make a choice of gamma to be less than and we can say that, well, as long as this happens, then this quantity is greater than this quantity. So, this is all negative, and we have a guarantee that the derivative is less than 0. That is what we are targeting, right. And so, that the derivative will be negative definite, and we can say that the nonlinear system is kind of asymptotically stable. Okay. So, so this gives you the first part of the proof. The other part, that when the origin is unstable, because at least if one of the eigenvalues have a positive real part, that will that proof requires an instability result. So, we are not going up to that. So, I hope this much is clear. We are able to show that, well, as long as we have linearized this nonlinear system, and the linearest part is actually satisfying the stability condition that A is Hurwitz with that means all the eigenvalues have negative real parts, then we can show that, well, the system is stable as long as this A continues to be Hurwitz like this. So, we have applied certain tricks here. For example, we have applied this continuity condition, we have applied this inequality using inequality of which relates the quadratic form with the eigenvalues, and with that what we can effectively do is we are able to calculate a value of this parameter gamma, which tells me that, well, for what choice this v should be negative, right. So, accordingly, then we are able to state that, well, in case we have linearized the system, and after the linearization, the matrix that we obtain, we have all the eigenvalues of negative, then the system is stable around the origin. Okay. So, fine, that is about our proof of this theorem. So, let us see this example here. So, suppose this is a system, and this system has an unstable equilibrium, okay, at x equal to 0. The system is stable at the origin for this value of A to be less than 0. So, if A is positive, then we have this unstable equilibrium, but if A is negative, the system is stable at the origin. I mean, intuitively you can see that actually, right. I mean, and in both the cases, when you have A greater than 0 or A less than 0, if you try to linearize the system, what you obtain is an equation like this, like x dot equal to 0. So, this is a situation where you cannot conclude anything from the linearization or the Lyapunov's indirect methods, but if you use the Lyapunov's direct method. So, what does the indirect methods effectively tell you? They try to provide you with an idea that how to choose the candidate Lyapunov function. Like in theorem 3, we say that, well, for a linear system, this should be your choice of Lyapunov function, and this inequality, the matrix Lyapunov function, the matrix Lyapunov equality must hold, etc., etc. And in the linearized case, we show that, well, for if you linearize and if the matrix is Hurwitz, then well, the same Lyapunov function will actually guarantee, I mean, the similar structure of Lyapunov function with suitable choice of parameters will actually guarantee that the system is stable. So, those are like directions which tell you that how to pick up the Lyapunov function. So, that is why it is an indirect method. The direct method is that you directly go and choose the Lyapunov function. So, we see that this is a system where we cannot apply the indirect methods. That means we cannot apply to linearize, we cannot also, and this is not a linear system that I just directly apply the matrix Lyapunov equation, right. So, those methods do not work, because if I linearize, then I have this, and also this is a nonlinear system. So, the matrix Lyapunov equation is not directly applicable also. Okay. But if I use the direct method and I somehow just arrive at this choice of this as a Lyapunov function, then you see that if you take a derivative here, okay. So, let us see what you get. So, this is basically a derivative of x, right. So, times x dot, right. Sorry. So, then you have x dot here. So, that is a times x to the power 6, right. And if a is negative, you can actually show that well this system is globally asymptotically stable. Around this unstable equilibrium point. I mean, it was unstable for this, but when a was positive, but we took a as negative, and then we said that we will take this as the function, and then we get this as the derivative. And if you take the second case, that a is less than 0, then we can show that well, since this is my function and this is the derivative and a is negative, we can actually demonstrate here that this system is globally asymptotically stable at the origin for this choice of a being negative here. Okay. So, more or less that is about our coverage on Lyapunov functions, and let us now move over to something different from this. So, ideally whenever we have been talking about Lyapunov function, it has always been about the stability of the system, right. But let us understand that well, while stability is an important property, we also need to talk about the safety of control systems. Okay. So, when we talk about safety of control systems, we use a notion called barrier functions. So, this is what we will study in the next lecture. Thank you for your attention.